Okay. So good evening, people.
Very good evening, sir.
That's a long time. Good evening. Yes. No, so this is like there are days when we don't see each other for 2 days, and then we see each other again in 40 minutes. Compensating.
Yes,
Okay. Okay. So proceeding ahead. We are starting with commutative people. Let's take an example directly. So there's a statement here, or I'll convert a statement into a question. So the question is, if two operators are Hermitian and their product is also Hermitian, then the product or then the operators, suppose I give you options: commute, anti-commute, don't commute. They do not commute basically. Sorry, they do not commute. And D is the bakwas option where they say information is insufficient. Okay, so let's check. So what do we have? If two operators are Hermitian, Hermitian means the operator A cap is equal to A cap dagger, and the product is also Hermitian. So two operators are Hermitian, A cap is also Hermitian, B cap is also Hermitian. Okay. Now let's define the product. So P cap is what A cap B cap is. Product is also Hermitian. It means P cap is equals to P cap dagger. It means A cap B cap is equal to A cap B cap dagger. It means A cap B cap is equal to, how do you write this? Double order. Okay, B cap dagger, A cap dagger. But A cap B cap is equal to B cap. Yes, B cap dagger is nothing but B cap, and A cap dagger is nothing but A cap. So A cap B cap is B cap B cap. This is commutation relationship. So they commute with each other. Next, it was a statement converted it into a question. Chalo, proceeding ahead.
Sir, 1 minute please wait, copying, sir.
Take your time. Disturbance, I cannot hear you. The earphone disturbance probably. Too much of noise. Where's my I'm working on Wi-Fi right now. Wi-Fi is back. Noise, too much of noise. Shall we done? Shall we? Try removing your phone. I think that is due to the earphone. Okay, next. Please learning properties for commutators. Okay, so many properties we have been learning. Next, number one, linearity. So A cap, comma B cap plus C cap. You can anyway split it. Okay, you can write that A cap, comma B cap plus B cap, comma C cap. Well, like, you can always verify this by taking an example. So that's fine. So there's a question here. Sir, if one is Hermitian and other is anti-Hermitian, how does we can create questions like that? No? So let's see. I mean, try check yourself. Make one.
So which properties are you discussing right now? Properties of
commutators, absolutely.
Okay.
Properties of commutators.
Sir, the B in the second one should be A.
Yes, thank you. Absolutely. I mean, obviously. Yes. Okay. So where was I? A cap into B cap, C cap. So it's basically splitting them like a distributive property only. So A cap, comma B cap plus A cap, comma C cap. Okay. Yes. Good observation. Next. Distributivity. And that is A cap, comma B cap, C cap. Okay. This is important. You need to by heart this rule. Why this exists? It's simple. You will have to take an example and check. Okay. So this is A cap, B cap first, and then you have C cap, and plus B cap into A cap, comma C cap. Why this exists, you have to take an example and check something. There is no other way to understand this. Okay, but you need to remember. So first A cap B cap in the commutator, then multiply that with C cap, and then like A cap and C cap in the commutator, and then multiply it with B cap. That's important. Okay. Similarly, there is another distributive property where we write A cap B cap and then C cap. You have a different rule altogether there. So here we have A cap into B cap, comma C cap. Okay, plus A cap, comma C cap into B cap. Again, why it exists? We'll have to take a random example, give A cap a value, B cap a value, C cap a value, and check people. I'll just confirm this. Let me see A cap, B cap, C cap, A cap, B cap, and C cap. A cap, comma B cap, C cap, B cap, B cap, C cap, B cap, B cap, C cap, A cap, C cap, B cap. Whatever. Okay, because I personally have never had this. So next, proceeding ahead. So that's all that we need here in commutators. Number 16. Okay, now I will use some operator relationships. I hope you have copied this much. Tell me if not, please. Okay, so first let's learn the two most popular variables in quantum, which is position and momentum. Like Heisenberg uncertainty also starts with that now. Okay, so position operator is position itself, nobody else. Okay, y cap is y, z cap is z. Position operator is position itself, nothing else. However, the momentum operator, please by heart, it is minus I h cut dou by dou x. P cap y would be minus I h cut dou by dou y, and P cap z would be minus I h cut dou by dou z. People, what is 1 upon I? I saw this number. Minus I. So minus I can replace as 1 upon I. You can also write this as h cut upon I dou by dou x. You can also write this as h cut upon I dou by dou y. You can also write this as h cut upon I dou by dou z. But my favorite is this. I go with this. I don't know. I'm more comfortable with writing it. Writing I in the numerical. Okay.
Yes, I do.
So remember these two operators as of now. Also, I'm just thinking, not sure if I want to write operator of the total function. Just thinking. So can I write it minus I h cut del or not? Don't write it up. Del would be I cap dou by dou x plus j cap dou. Yes, absolutely. No, then this becomes px, dy, and pz. Yes, okay. So people, this p cap operator, just p cap, which is the total operator. I can write this as p cap x plus p cap y plus p cap x I cap. This is total operator. No. Similarly, you can have p cap y j cap plus p cap z k cap. Okay, and we can write this as minus I h cut del operator. Because what is del operator, people? It is I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. No? So if you substitute this here, you will get px will be this, py will be this, and pz will be this after comparison. Minus I squared dou by dou x minus I squared dou by dou y minus I squared dou by dou z respectively, px, py, pz. So that's just p cap.
So p cap equals to px cap I cap or px I cap plus py j cap plus p cap.
No, px cap. This is operator. This is p cap, not px or p operator. This is px cap, px operator. And I cap is unit vector. These are unit vectors. These are not operators.
Okay.
These are unit vectors. Okay. Confused or understood? Just like p vector is px, I cap, y, cap, p vector. So these are unit vectors. These are not operators, but we denote them also by a head. So okay, no problem. But main I want you to remember is basically p cap. P cap is just minus I squared. That's it. Directly remember this.
Del is a gradient.
No, not gradient. You call it del operator. It will be gradient if you apply it on scalar. So
Okay.
if you apply del on a vector, it becomes a curve. If you apply it, it could also become a divergence also. It depends. If you're applying this on a vector, then it depends. But if you're applying it on a scalar only, then you call it a vector. As of now, we just call it a del operator. So let's calculate a few things in this. I hope you are comfortable so far. Tell me if not. Let's calculate commutator of x cap, comma p cap x. It's a question in itself. Never calculate it directly. Even though they ask you the value, I have told you this. You will apply wave function first. Basically any function. Okay. Now substitute. What is operator of x cap? X itself. And what is operator of p cap x? Minus I h squared dou by 2x. And now open the brackets. A comma b. That's ab minus ba. So that's ab minus ba. Take care of minus of minus ba. Okay. Into psi. But don't open this yet. You can throw minus out, that much is fine. But remember, first you have to take psi inside. First you have to take psi inside. So don't calculate anything yet. Just keep it minus, you can throw, that's fine. So minus x I h squared dou by dou x minus plus I h squared dou by dou x into x. Now I'm throwing psi inside. Have a look. I'm throwing psi inside, psi here and psi here. And now you know the rule. First you have to multiply psi with this, and first you have to multiply psi with this. Or if you want to get this, put the brackets. If this is still not comfortable, just open the brackets. Keep the operators as it is. Keep the operators as it is. Just open the brackets. Don't do anything. Just don't do anything. Keep the operators as it is. So first operator, second operator function. First operator, second operator function. You know the rule. First you will apply this to the first operator, this operator, and you'll apply this to this operator. That's how we are going to start. Okay. So this is x into. So if I apply psi to dou by dou x, that's dou psi by dou x. So what do we have? Minus I h squared dou psi by dou x. That's fine. Okay. Minus plus. That's okay. I h squared into dou by dou x of. Now x into psi. That's x psi. Now you have to apply the operator on the total function, people. Here also will apply the operator on the total function. So I applied x on the total function. I applied this on the total function. I hope you are with me. Okay. We copy this much understanding by I think here.
Sir, third step में आपने वो formula use करा क्या आपने?
AB minus B. Yes, AB minus B. Yes. And if square bracket is confusing, convert this into some other bracket because we already are using square bracket for commutators. So maybe you can just use some, let's say, curly bracket. That's anti-commutator. What should we use? Okay, let's use this. Okay. If you use square, that's commutator. If you use curly, that's anti-commutator. We are just left with this. Okay.
सर एक से बात कर दिया साई गाय
Sorry. Sorry. Okay. Even just you are smart enough. I trust you all. You notice. Chalo. Proceeding ahead.
So just a minute.
Take your time. Sure. Understand and right, please. Don't compromise. Don't hesitate. So people, after exam, you have 1 month of break before you're having just paper. Okay? In just commutator is a very important topic. Use Zetli to refer. Okay, later. We are not covering a lot in commutator. We are just covering some little things which I feel will be significant to study the respective later chapters. But one questions are always asked from this topic in that exam.
Okay.
And I hope you all have filled just form already. I
Yes.
think only 2 weeks is remaining or 10 days are remaining to fill, or 15 days, whatever. I don't remember the last date. Fill it earliest,
18th January.
18th January. Okay, you have a lot of time. Proceeding ahead. Let's solve this further. Now it's fine. So now throw x, like multiply this operator with this total value that you have got. That's time pass now. Minus I h squared x dou psi by dou x. And plus I h squared. Now the thing is, derivative of this whole function people. So that's uv, first constant derivative of second, the second constant derivative of first. So first constant derivative of second, you have I h squared again, don't forget. And then second constant derivative of first. Partial derivative by the way. Partial derivative. Okay, I h squared is also there. So I h squared into the uv rule of this. What do we see? Minus I h squared x dou psi by dou x plus I h squared x dou psi by dou x gets cancelled. We just are left with I h squared psi. What is the derivative of x with respect to x? 1. We just have I h squared psi people. Okay, so the value of x p cap x psi is I h squared psi. X cap comma p cap x psi is I h squared psi. So you can cancel psi and you can equate the commutator value. You can find the commutator value from here. Clear? I cannot hear anything, only noise. Okay. So x cap comma p cap x. This value is equal to I h squared. That's it. Because at the end psi you can cancel on both sides, so you can basically equate the commutator with the constant. Basically, this is like an eigenvalue relationship. You have an operator, you applied it on a function, you got the same function back. This is the eigenvalue. Simple. This is an eigenoperator. Commutator itself is an eigenoperator. Okay. Why it's an eigenoperator? Commutator is what people? It is a cap, b cap minus b cap. Product of two operators is an operator. Product of two operators is an operator. Operator plus operator, operator minus operator is also an operator. This whole thing is an operator in itself. Call it z cap. So you have applied an operator on a function. You got the same function back. So this is eigenequation people, and this is an eigenvalue. Okay. And now here I can use my favorite word in physics in the chat box. So if the two operators don't commute with each other, we don't find their values simultaneously. Well, so about that, that's what I said. This is related to Heisenberg's uncertainty, but okay, you got the gist of it already. But we will come to Heisenberg's eventually. But yes, you are close to what you said. Okay. So proceeding ahead. My favorite word, similarity. Okay. Which I just said about. I can write y cap comma p cap. It is I h squared. And z cap comma p cap z. It is I h squared. Because nothing will change. These are arbitrary notations. Just replace x with y everywhere, then you get the same result at the end. Okay. Next. Such a beautiful word. Thank you, English, for discovering this. Okay. Proceeding ahead, people. Shall we?
No,
Next.
sir.
Okay, right. Take it. Which are your favorite words in English or the sequence? Like similarly is there, then same to you. One of the best. Same to you. You don't
Yes,
have to
sir,
like
yes,
again and again. Take it. Next. So now let's calculate x cap square, comma p cap x. Okay, the value of this. So again, we won't multiply them directly. Now I think by the time it's hammered in your head already, you always have to apply wave function. Nicely hammered, I think so. So now x cap is nothing but x. Good. And p cap x, that's minus I h cut dou by dou x into psi. Let's multiply. So x square into minus I h cut dou by dou x, a into b, minus b into a. So minus b into a. So this is a cap, minus b cap, the whole into psi. Okay. Now we will throw psi inside. So if I throw psi inside without disturbing the operators, first psi will multiply to the derivative directly. And then minus minus plus, this is fine. I h squared dou by dou x. Here I will multiply with x. Here I will multiply with x. That's important. Copy. Be honest, if you have any questions, don't hesitate, please. So Dora, what you just said, that is the importance of commutator basically. Why are we learning commutators? That's the only importance. हाँ बोलो.
x square आएगा ना x आएगा.
हाँ, x square आएगा ना, x square. Absolutely x square. Absolutely. ठीक है. I was only checking. Who is active? Done, people.
Done, sir.
Chalo, next. So what do we have? Minus I h squared x square minus I h squared x square into dou psi by dou x. Okay. Plus I h squared into, now you will people, first constant derivative of second, second constant derivative of first. So x square constant derivative of psi, you have I h squared, don't forget that. Then psi constant derivative of x squared. Okay, these two terms are getting cancelled. Beautiful. Nice. So I h squared psi derivative of x squared, that's 2x. So I can write this is 2I h squared x psi. So what is the answer, people? On the left hand side you have x cap square comma p cap x. No? So we have got into psi. So you can basically cancel psi. You have got commutator option. People. Basically again eigen operator. This is your eigenfunction. You can say eigenvalue, and this is your eigen function. Or you can say this is operator also. Like call it eigenvalue, but this could be an operator also. Like you can write this, you know, 2I h squared x can be taken as x cap. So you can also say operator is operator, whatever. Okay. So what do we have? X cap squared comma p cap x. This is 2I h squared x, people. Can you generalize this? I'm thinking. We have calculated xt, that's I h squared psi. But now I have 2I h squared x.
Sir, x की power आ जाएगी.
X की आंसर है.
Ask Sakti, we need another example to check. We need another example to check. I think we can have.
Maybe a general case. Like
So right now we have x raised to 1. We may have x raised to 2. I think we will now because x cube, that will be 3x squared.
Yes, sir.
Okay. So let's quickly check this quickly. So what do we have? X cap cube, comma p cap x. I love generalizing. I don't even need to. Multiply this with side. So calculate. You calculate.
Sir, सीख गए आपके साथ.
Alright, nice. Calculate. Take your time. Have patience.
Sir, 3i h dot x square होगा.
Outstanding. Chalo, jalsa karo. So what do we have? X cap raised to n. You know, I said jalsa karo, what is the meaning of it? I just spoke Gujarati basically. Jalsa is like half one. Okay. So x cap raised to n, comma p cap x. So what would that be in general?
n I h f power n minus 1.
Perfect. Chalo, nice. Let them ask this in exam. Such a scoring one. Okay. Achha, so because we did this, what if p power x cap does not have power? I mean, we can do this time for all the time. But let's take an example on p cap also. Let's give p cap also a power and see what do we get. Okay. Done, people? Any questions, anyone?
Done, sir.
Please tell me if you have a question. Okay. So the first value that we had got was x cap comma p cap x. That was just I h squared, just I h squared. And then you had multiple values. Okay. Now let's just calculate what happens if I have x cap comma p cap x squared. This one has a square value. Okay. Then what can happen? Okay. So this is x cap comma p cap x squared into psi. X cap is x. P cap x is minus I h squared dou by dou x the whole square psi. But now we have I now. That's the problem. But okay, let's see. So we have x. We need to check a couple of more values. But okay. So x comma minus square is plus, but I squared that's minus 1. I squared is minus 1. Okay. And then you have x squared and you have derivative. Oh, yes. I'm thinking.
ये तो नहीं होगा सर, स्क्वायर
सर इसमें नहीं होगा शायद.
क्या नहीं होगा? Relationship?
डेरिवेटिव का.
सर सेम नहीं है.
अच्छा, are you saying the second derivative नहीं होगा?
Yes, sir.
नहीं होगा. होगा ना? Because we have got. But what the thing is, square will happen because we have a minus I squared dou by dou x into minus I squared dou by x. It is square, derivative of derivative. But because these are two operators, I think I should not multiply them directly. We are not sure whether we have same relationship or not.
Yes, sir.
We can write this in general, like in mathematics we do. This is actually second derivative only. But right now I'm thinking we should not do it like this. Okay. So what we'll do is, this is comparatively more challenging right now, but okay. So let's split this because right now we are not 100% sure whether we should split them or not. Let's keep it like this then. I don't think it will affect the result, but okay. So it will be second derivative. Dou by dou x or dou by dou x. It will be second derivative. Okay. I think it's fine because this will go to this and then you will get second derivative. No problem. So let's write this further. So what do we have? AB minus BA. So we have x into minus I squared dou by dou x. Okay. Into minus I squared dou by dou x. That's AB minus BA. So minus of minus I h squared dou by dou x minus I h squared dou by dou x into x. So okay. This is B. This is A. A into B. And this is B into A. The whole into we have psi. The whole into we have psi. So I'm just going to throw psi inside right now. So let's throw psi inside, people. So I have psi here and I have psi here. Okay. So what do we have? Minus x I h squared dou by dou x. Minus also you can go outside, so minus minus is plus. That's fine. I h squared dou psi by dou x. See, you are getting second derivative. So minus 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 3 minuses. Okay. I h squared dou by dou x. I h squared dou by dou x of x into psi. Okay, of x into psi. That's fine. So what do we have? I can do I h squared also outside. X into I'm showing I h squared outside. So I squared h squared square. Okay. I squared h squared square. We have dou square psi upon dou x square now. Okay. Minus again I squared h squared square. We have dou by dou x of xi and dou by dou x of this. So this is basically dou square upon dou x square again of x side. Okay, so let's do one now. Let's calculate individually only. So dou by dou x. Let's calculate xi. What is xi? Like derivative of this. First constant derivative of second. Second constant derivative of first. X constant derivative of psi plus psi constant derivative of x, which is 1 by the. I'm writing 1 directly. Okay. Patiently copy this. Must understand and write once again. Don't hesitate. Don't rush. Tell me if you have any questions anywhere. Done, people.
Yes, sir.
So let's calculate what do we have. X into I square, that's minus 1. Okay. H squared square, that's okay. Dou square psi upon dou x square, that's okay. Now minus I square, that's plus. Okay. So minus I square, that's plus. By the way, write it here. So this is plus 1. Okay. Just open this now. H squared square, there is another derivative. Okay. Plus h squared square into there's another derivative. X dou psi by dou x. Sorry, wait. Too much of things. I've got another derivative dou by dou x of x dou psi by dou x plus psi. X dou psi by dou x plus psi. People, this is easy. It is just that this is exhaustive. It's not difficult. Okay, plus h squared square. Open the brackets. Again, UV rule. That's okay, time pass. So what do we have? First constant, derivative of second plus second constant, derivative of first, derivative of x with respect to x, that's again 1. And then you have derivative of psi with respect to x. Have a look. X constant, derivative of this, that's second derivative now. And then dou psi by dou x constant, derivative of x, that is 1. And then derivative of psi by x, okay? Open the brackets. Two terms are getting again cancelled. This term and this term are getting again cancelled. Minus x h squared square dou psi by dou x plus x h squared square dou square psi by dou x square. They're getting cancelled, okay? We just have h squared square. We just have h squared square dou psi by dou x plus dou psi by dou x, which is 2 dou psi by dou x. Nice. So this is 2 h squared square dou by dou x of psi. Okay. P cap is minus I h squared dou by dou x. No? P cap square is h squared square. But we have, okay, we can have dou by dou x raised to n minus 1 dt. There is a relationship which I think is possible here. Only thinking, but not sure. Copy this much. But it will be tedious us to check for x cube.
Yes, sir. Multiply.
I think there is a formula on this directly. Let me just find this. Hang on. And we'll verify for answer is correct or not. Give me a minute. Maybe it's in one of the book. Just a minute. There is a general formula on this. Hang on. Okay, found it. Hang on. So let's, we'll check our answer is correct or not, but the formula is something like this, people. X cap, comma, P cap x raised to n. See, even we can generalize this, but I don't want us to invest that much amount of time in checking the third one also. But without checking third one, we won't be able to generalize it directly. So you can do it for your practice, see if you're getting this or not. Ni h squared upon P cap x raised to n minus 1. Okay. So let's see if using this are we getting the answer or not. Okay? So what do we have? We have got x cap, comma, P cap x squared. We calculated this now. What is our answer? 2 h squared square dou psi by dou x. I mean dou by dou x. Our answer is only this one. Psi and then gets cancelled from both the sides. So 2 h squared square dou by dou x. 2 h squared square dou by dou x. Okay, let's see if we're getting this or not. So n is the power p. So this was expected. This we assume. Then I have got I. Okay, and I have got h squared. P cap x. What is P cap x? Minus I h squared dou by dou x. Okay, raised to n minus 1 people. So n is 2 now. So raised to 2 minus 1. So we have got 2 I h squared minus I h squared dou by dou x. What is 2 minus 1? That's 1. So minus 2 outside. I into I is I squared. H squared into h squared is h squared square dou by dou x. We have got minus 2. What is I squared? I squared is minus 1 now. Outstanding. We got the result.
Yes, sir. See.
Okay, good. Okay, so if you are good at memorizing, you can memorize this. But this one would be difficult to analyze, I think so. Okay, because so what we are doing constantly is, we are getting rid of I people. Wherever we have I square, I cube, we are calculating them. And in the final general formula, they have kept I, if you realize. They have kept I here and they have kept I inside. So what we understand from this is, if you want to create a general formula, don't mess with I. Keep I as it is. Wherever you find I, all the I keep I as it is. I square, I cube. Wherever we put I square as minus 1 now, don't do that while calculating general. In that way only you will be able to get this general formula. I hope you understand what I'm trying to say here. Don't play with that. Keep I as it is first. That way you will be able to derive the general formula by yourself if you want to do that. Yeah. So you will observe something like this. Basically, your pattern will be ni h cut minus I h cut dou by dou x raised to n minus. So you will see this kind of a pattern. That will be very interesting to see. But in that case, you cannot touch I. You have to keep I small, probably. But interesting, actually got the result. So that's good. Done, people? Any questions?
Yes.
Anyone? Okay. So hang on. It's good. Okay. So I want you to also find commutator of x cap comma y cap. Find this. Let me search something in mind. Commutator and Heisenberg's uncertainty. I want to relate this with it right now.
0.
Zero, absolutely zero. Okay. This is
Zero.
it. Yes. Heisenberg uncertainty with commutator. Images. Okay, so chalo. Now I want you to understand the importance of what did we just learn. So this value is 0, as you have found out by the way. So Heisenberg's uncertainty principle can be expressed in commutator form. People. Okay, so any variable of Heisenberg, sigma A into sigma B, basically a cap, like any observable you're talking about. Okay, so this is always okay. Forget sigma, we will write our notation. What do we know? Like error in x. So suppose error in value of A into error in value of B. So this will always be greater than or equals to mod of 1 upon 2i, mod of 1 upon 2i into average value. Average value. Okay. Not sure why we have average value though. Okay, of a cap, comma b cap. The operators corresponding to the two observables. You know, people, this is position. Suppose so position operator, momentum, the momentum operator. Okay. So average value of the operator mod square. Let's verify this if you are getting this or not. Make a note of this. What
Sir,
is
x cap और y cap जो है वो पोजीशन वेक्टर्स है ना, तो x y is always equal to y. That's why it's in cancel.
Yes, absolutely. Yes. Like first you need to apply this property. So this is x comma y, and then you apply this into psi. So you will have xy minus yx into psi. So you will open the brackets xy psi minus yx psi. Nothing is happening here. All of them are simple variables, simple scalars. That's it. So obviously they're getting cancelled now. So they will give you. Okay. So people, we have calculated x and px, and we know the answer by the way. What is delta x into delta px? It should be greater than or equal to x cut by 2 now. We know this. Let's verify. Okay. Delta a, delta b. So delta x, delta px should be greater than or equal to mod of 1 upon 2i. I'm not sure what the average value means here, but let's check. Okay, average value of a cap comma b cap. What is a cap comma b cap? That's commutator. Commutator of x cap comma p cap x. Okay, average value the whole square. So this is greater than or equal to 1 upon 2i into average value. What is x cap comma p cap x? 2i square.
I
I square.
minus I
Minus I square. Right. Okay. So the whole square. Average of minus I square. This is anyway constant, so it will remain minus I square. So no problem there. So delta x, delta px. This is greater than or equals to 1 upon 2i into. You can throw minus I square outside. Okay, the whole square. I gets cancelled. So what do we have? X squared by 2. Minus, but then we are getting unnecessary square also.
minus I क्यों?
I don't know. She said minus. What is the value? Is it I squared or minus I squared? I don't remember.
Only minus, only I got.
Only I squared, no? Okay, so only I squared. I don't remember.
Yes, sir. I thought.
Okay, it's fine. So this is x squared by 2, but why are we getting square then? Hang on, we shouldn't get square now. Why are we getting square unnecessarily though? It may be incorrect formula also. Let me check another book. I mean another page. Yeah, there is no square. Sorry, chalo, nikalo. There is physics 3 for electrical engineering PPT video online that I'm referring. There is no square at all. Okay, so please remove the square, people. Please remove the square. Okay, basically I have just searched on Google right now. Heisenberg's uncertainty principle with commutator. Somebody had written square there, but that was handwritten. Everywhere else it's not it. So remove it. Okay, so we got the result now. That's the best part. Delta x into delta px. This is greater than or equal to x squared by 2, as expected. Now listen. What does Heisenberg's principle tell us? That these two values can never be calculated simultaneously. People, if this value becomes 0, then what does it mean? They can be calculated simultaneously. Now, if it becomes 0, it means they can be calculated simultaneously. If h tends to 0, that is classical mechanics. Now, h tends to 0, it means no uncertainty whatsoever. You are in the classical world, we have learned this. It means everything can be calculated simultaneously. There is no problem with the classical world. Okay, so right. So tell me one thing. For this to become 0, go in the reverse direction. Who should become 0? Commutator? Hello?
Yes, sir.
Please repeat what you're saying.
Okay, so this is Heisenberg's uncertainty principle. Like what does it tell us? That x and px can never be calculated simultaneously with accuracy. If you are calculating this 100% with 100% accuracy, if delta x is 0, then this becomes infinite. Because then it's not 0, that becomes infinite. So this will have infinite error. So point is, we can never calculate these two values simultaneously with utmost accuracy. There is always an error. Understood that?
Yes, sir. After that.
So there is always an error. Now, so when will we not have an error? When the product of this will become 0. So suppose if this becomes 0, it means we have calculated the values with utmost accuracy now, and without ensuring that other is becoming infinity. So if RHS is 0, and other is not becoming infinity, like delta x into delta px, if this is 0, it means somebody has not become infinity. That's good for us. Okay. So we have calculated the values without saying that if one is accurate and another is infinitely accurate. So in order to destroy the idea of quantum mechanics, so in order to go back to the classical world where everything can be calculated simultaneously, basically when h tends to 0, it means when h tends to 0 also. When will RHS tend to 0? When this tends to 0, when this tends to 0, when this tends to 0, when commutator will become 0. Correct?
Okay, sir.
Hello? So we can simply say that
They can use it.
x and px can, like not x and px, basically any two vectors, a and b, can be measured simultaneously if they commute with each other. People, simple. A very beautiful application, okay, of commutators can be measured simultaneously if they commute with each other. So can I ever measure x cap and p cap x together simultaneously? I cannot now. So they don't commute with each other, which we know they don't commute. I get it. Can I calculate y cap and p cap x together? No, we cannot. We know there is uncertainty involved, and hence they cannot commute with each other. So if they don't commute, it means uncertainty always exists. Okay. If they don't commute, it means uncertainty exists. Simple. Understood this, people? So far, you can x and y commute with each other. We just calculated now. It means you can measure x coordinate and y coordinate simultaneously. There is no problem there. You can measure x and y simultaneously, but can I measure x px? No. Can I measure y py? No. Can I measure z pz? No. I cannot measure these properties simultaneously ever. I hope
The
understood.
operators must not commute, right? The
Operators,
operators.
operators corresponding to these observables. So when you say they, it means their operators. Let's make this proper English. So if their operators don't commute, uncertainty exists. And here also, if their operators, corresponding operators, if their operators, to be more precise, we can also write corresponding operators. Okay. A very beautiful way to find. So whenever people in physics, you will check, like if you will see that uncertainty must exist. It means the two operators cannot commute with each other. Like a cap into b cap will never be equal to b cap into a cap. Uncertainty will exist here. And if you say that uncertainty does not exist, if they can be measured simultaneously with accuracy, okay? With accuracy, if they can be measured simultaneously, okay? It means they commute with each other. A cap b cap will be equal to b cap b cap. This is the only major application of commutators. Any doubts? Anyone? Anywhere?
So please back to the last page.
Sure.
So here that is modular small sign.
That's mod, and hence minus. Like capital you have minus, it will come plus. Yes.
Okay.
This is mod. Yes. Okay, people. Any questions? No. Okay. So just telling you, just asking. So logically, because x and y do not commute, even p cap x and p cap y should also do not commute. You can practice this if you want. Just calculate p cap x, p cap y. You can calculate two momentum along two perpendicular directions simultaneously. There is no hesitation there also. There, Heisenberg uncertainty principle again is not valid. You can measure them simultaneously. See if this becomes 0 or not as an exercise. And during this, you will need to use the derivative of property, which you have got like dou square upon dou y dou x. This can be written as dou square upon dou x dou y. No? You have not this. Shuffling is allowed in partial derivatives. So you can use this. Okay. So after this, I need you to by heart Hamiltonian operator. Hamiltonian operator. Which is energy operator, by the way. Energy operator is known as Hamiltonian operator. Because Hamiltonian was the guy who came up with this. It is nothing but p cap square upon 2m plus v cap. Obviously, kinetic energy plus potential energy. Okay. Kinetic energy is what p square upon 2m, and potential energy is v. V cap is nothing but v. V cap is v. So for example, if you are doing, let's say, spring energy, so v will be what? Half kx square. If you are doing, let's say, 1D harmonic oscillator, there also you learn the value of v respectively. So then give you the value of v. Just giving you an idea. V is nothing but potential energy. So v cap is v, x cap is x, y cap is y, v cap is v. P cap, you know, P cap you are already aware of. Okay. So this can be written as 1 upon 2m. What is p cap, people? Minus I h square dou by dou x. Okay, the whole square plus v cap. So this becomes 1 upon 2m minus square is plus I square h square dou square upon dou x square plus v cap. Okay. So we have got h cap is equal to what is I square, people? Minus 1. So you have got minus h square upon 2m into dou square upon dou x square plus v cap. I think you have seen this somewhere in BSc, haven't? This thing.
Yes, sir.
What is the
Yes, in Schrodinger equation. So from where does Schrodinger equation arrive? Do you have any idea?
oscillators है sir?
Hey, two-line derivation. See, I'm not sure what derivation you have taught in BSc. It's a two-line derivation provided you have learned commutators and operators.
Hamiltonian.
I multiply कर देंगे.
That's it. Hamiltonian operators, people, are eigen operators. What is the meaning of that? That if you apply h cap on psi, you should get eigenvalue. Which eigenvalue? Will I get position? Will I get momentum? Which eigenvalue will I get?
Energy.
Energy. Because this is an energy operator into psi. What is h cap? Minus h square upon 2m. Minus h square upon 2m. Dou square upon dou x square plus v into psi. This is that. This is the Schrodinger equation. I'm not sure what derivation you have learned. It's a two-line derivation provided you have learned this. Okay. Nice. Huh?
So that's the double derivative. Del square.
Yes, double derivative. Absolutely, yes, double derivative. So
And
like
v cap में कुछ नहीं है, मतलब वो हमें given होगा या फिर
they will give us like if they will mention free particle, so no potential energy, no direct, zero. In that case, it's zero. And if they mention that it's something, I don't know, they have to give us basically like spring energy, then half kx square, like I said, or gravitational energy by any chance if they want to include.
so v cap is equal to the expression of the potential energy.
Absolutely, this potential energy only, just like x cap is x, v cap is v.
Okay.
It's a scalar here. There is no derivative, no operator as such. V cap is v itself. Okay. You can write down for free particle potential energy, no interaction. Free means what? No interaction, no potential energy. So for free particle, the value of h cap, sorry, the value of v is zero. Okay. So in that case, h cap will be just equal to minus h square upon, minus h square upon 2m into dou square upon dou x square. In that case, for free particle. But like I said, this is a time independent Schrodinger equation. There is no time involved right now. So write it as TISC, time independent Schrodinger equation. Remember, Hamiltonian operator is an eigen operator because I'm using an eigen equation. Who said that psi will be psi? Hamiltonian is an eigen operator. Make a note. Hamiltonian is an eigen operator because function does not change.
So can I go to previous slide once?
Sure. With the background noise.
So we are starting from p cap equals to minus I h square del x. So is there a derivation to get that, or that is the
Hamiltonian operator.
No, Hamiltonian, not the momentum operator, that is p cap.
Acha,
minus I h square del x.
see, there has to be a derivation, but I personally have not learned how do we get these operators. Even the h cap value, h cap is logical by the way. H cap is completely logical, standard equals potential. P cap, now I'm thinking, I'm not sure what can we use for momentum, mass velocity, but it's not related to mass velocity. There should be some logic behind getting this. No, but I've never wondered about it.
Okay, sir.
Yes, we can always search anyway. That derive.
Yes sir, it be. Our college.
Acha, so there is a derivation related to this, right?
Yes sir.
Right. There has to be something using which we find this. So yes. Okay. Next, proceeding ahead, people. Can you find okay? So there is a question again related to this only. I want to take. Acha, by the way, commutator with this I'm ending. A commutator part is ending, but listen. So commutator can be expanded a lot. You can learn angular momentum commutators. Angular momentum is what L vector R cross P. How do you calculate those Lx, Ly, and Z by taking determinant I cap, J cap, K cap, X, Y, Z, P, X, P, Y, P, Z, cross multiply, compare, and everything. But all of this is not at all required for our JAM syllabus at least. For just, it's easy to understand from any standard book. So you can, if you can learn after JAM, we're ready to do some. But our syllabus related to commutators, this is it. Okay.
So one question.
Haan ji.
So we have till the h equals to minus I cut square by 2m del square by del x2. So it can be del y2 or del z2 or so.
I mean, it depends on when we are oscillating. Like we usually assume that we are oscillating along y-axis. If it's y, then it will be y. But in that case, listen, you need to understand. If this is x, it means potential energy is also a function of x. Psi is also a function of x here. Okay. But if this is y, then all of them must be a function of y. If it is x, y, z, in that case, you have to write del square. In that case. Okay. That's obvious. So let's take a question just a minute. So this this one. Okay. So we have a question here, and that is ax e raised to minus x square by 2 is an eigenfunction of h cap. Okay. What is the associated eigenvalue? Given that potential energy is cx square. Okay. Or wait, how much cx square and hang on. I will directly write this. Wait. Given that Hamiltonian operator basically this h cap that you have is minus rho square upon 2x square plus x square. Okay. This is Hamiltonian operator which they have given us. Basically, they have said the value of h square upon 2m people, h square upon 2m, it tends to 1, and the value of the cx square that I was writing, c, also tends to 1. Okay. So Hamiltonian operator becomes this. H square upon 2m, that is also 1. Cx square, that also becomes 1. So that's fine. And options are options A, B, C, D. 1, 2, 3, 4. So let's solve this. Okay. So originally, like I said, v of x is given to us, which is cx square, and we know h cap is minus h square upon 2m into 2 square upon 2x square plus v people. So this is, they have said that this tends to 1. So I just left with this plus v is nothing but x square because c also tends to 1. That's it.
C means a constant, no?
It's a constant, it's a random constant.
And we're given that Vx
It's
equals
given.
Cx.
Yes, Vx is given to us. It's cx square. Yes. Okay. So let's solve this. You know what you're supposed to do. Eigenfunction. So it has to obey eigenequation. Apply h cap on the function, and you'll get the same function back with the corresponding energy, with the corresponding eigenvalue. So let's start with let's say this is a wave function given to us. Ax e raised to minus x square by 2. Ax e raised to minus x square by 2. Okay. And we have to, what we have to do here is we have to say h cap psi will be equal to an eigenvalue, some eigenvalue into psi. It must be some eigenvalue to psi. That is what should happen. Okay. That is what should happen. Okay. Okay. So we want to find the value of p. So let's apply h cap psi. Start with LHS people. We want to find the value of p. Eigenvalue we want to find now. Eigen operator into eigenfunction. This is eigenvalue into eigenfunction. We want to find the value of p. So LHS, h cap psi. What is h cap? Minus 2 square upon 2x square plus x square into psi, which is ax e raised to minus x square by 2. Okay, it's not going to be that easy, but okay, let's calculate. I mean, it's easy but exhaustive. Once again, double derivative and two functions will have four parts of this, whatever, 4 terms. Okay, no worries. Let's do this. So let's start with the first derivative. Okay, minus dou by dou x of ax into dou by dou x of x e raised to minus x square by 2. I will just throw a outside immediately. I'm sorry. I'm throwing a outside. Dou square upon dou x square into, let's say dou square upon dou x square as dou by dou x of dou by dou x. Okay, more better. And then I have x e raised to minus x square by 2. I've just thrown a outside, nothing else. Plus x square into ax e raised to minus x square by 2. Copy please.
So one question.
Well,
so we are writing operator one after another. Is there an official rule to get the bracket in between them or not? That you have to do?
No. But just remember, like I have got, apply to the first, and if you have another, then apply. Otherwise, don't worry about anything else. Just take care of the steps first. Okay, next. Otherwise, don't worry about how to put the bracket and everything. That's too technical. Proceeding ahead. What do we have? Minus a derivative into. So UV rule. Okay. First constant derivative of second. So derivative of e raised to x, that's e raised to x. Derivative of e raised to minus x square by 2, that's e raised to minus x square by 2. But I have to redifferentiate this. If I redifferentiate this, I have minus half outside, and derivative of x square is 2x. Any questions? Plus second constant derivative of first. So if I keep second constant, if I calculate derivative of x, that is 1. Okay. Plus x square ax e raised to, okay, this is ax cube. This is ax cube e raised to minus x square by 2. This is directly ax cube e raised to minus x square by 2. Okay. Further, so we have minus a into dou by dou x of 2 gets cancelled. X into x is x square e raised to minus x square by 2. There is a minus sign also. Hang on. Minus x into x is x square e raised to minus x square by 2 plus e raised to minus x square by 2 plus ax cube e raised to minus x square by 2. Okay. Let's
No, sorry. Okay.
No problem. So we have minus a into, once again, apply derivative. So minus outside, x square constant, derivative of this term. Derivative of e raised to x is e raised to x, but I have to redifferentiate this. When I redifferentiate this, I have minus half and 2x. Minus. There is a minus sign, don't forget. Second constant, derivative of first. What is derivative of x square? 2x. There is minus, don't forget, first constant derivative of second, minus second constant derivative of first, okay? Plus e raised to minus x square by 2, plus ax cube e raised to minus x square by 2. Okay, so these are getting cancelled. Good, great, nice, outstanding. We got the result, I think so.
So I have lost the floor. Would you be the last slide?
So should I go to the last slide?
Yeah, last line. Just
Last line? Sure.
Last line.
Okay, so no problem. So I have got minus x square. I'm then derivative to the first term. Derivative of e raised to minus x square by 2 is e raised to minus x square by 2. I redifferentiate this. So minus half derivative of x square is 2x. Done.
Yes, sir. Yes, sir.
So first constant derivative of second, minus sign again. Second constant derivative of first term, second constant derivative of x squared, that's 2x. So the first term is done. This term is done.
Okay. Okay.
After that I have the mistake. After that I have the mistake. Okay, wait. There is a derivative to this also, no? There is a derivative to this also. So which is e raised to minus x squared by 2 and then minus half into 2x. Now it's fine. And now I have to now this term as it is. Okay. So your question helped me to find the mistake. Any questions? See, keep asking questions. It helps me too. Are you alive?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Good. Proceeding ahead. So 2 gets cancelled. What do we have? Minus a into minus x cube e raised to minus x squared by 2 minus x cube e raised to minus x squared by 2. People have a look. 2x e raised to minus x squared by 2, x e raised to minus x squared by 2. We have total 3x e raised to minus x squared by 2. Take your time. You have got minus 2x and you have got minus x. So we have got minus 3x, okay? Minus 3x. Tell me if you have any questions. You have a better visual. You are writing this step after step. Minus 2x into this, minus x into this. So you have got minus 3x into this, okay? Plus ax cube e raised to minus x squared by 2. Open the brackets, people. The first term gets cancelled with this. Hey, it should now. There is a minus sign.
The first term should be minus.
This is positive. There is a minus sign here. Now it's fine. So open the bracket, the first term gets cancelled. We are left with minus minus plus 3ax e raised to minus x squared by 2. That's the final answer. Anyone? Any doubts? Anywhere? These two terms get cancelled if you open the brackets.
Yes, sir. Totally mathematics.
Total mathematics. So this is 3a. Wait, what is this whole term? Check.
That is I.
Okay.
Yeah, that is 3.
Absolutely. See, time pass question. Scoring question.
Yes, sir. Scoring.
Scoring, very scoring. But provided people have learned this. Provided that people have learned this. Okay. Chalo. Nice.
So the eigenvalue is 3.
Absolutely. No? And this on function, you get eigenvalue into function. Eigenvalue is 3. Answer was whatever ABC. Okay. So that's about commutator. And now let me see what I have to read next. Link water. Okay, the chapter is done. We are done with the mathematics for quantum mechanics. So we have to start with the new chapter, postulates of quantum mechanics. People, please go ahead. I think I should create a new slide, but we have 15 minutes. We can. Okay, let me just create a new slide. Just give me 1 minute now. That will be better. I will just document this out in a new folder. Okay, 30th December, lecture 15B. Let me call it B now. Share screen. Okay. Chalo. Here we go. So please give heading the new chapter, which is postulates of quantum mechanics. POQM. You know what is the best part, people? Now only 2 important chapters are remaining. Only 2 chapters are basically remaining where I have to complete everything. Postulates and application of Schrodinger equation. POQM and AOSE. And we have got at least 10 lectures. I think that will be sufficient to complete quantum mechanics nicely. I don't have to rush to do anything. And I think I might just get some double lectures at the very end also because search syllabus might also be completed. So no compromise on quantum. That's good.
Very good.
Yes, sir.
Hey, actually, the thing is, I thought we will have to, but I realized half of the modern physics is already taken. And not half, nuclear physics, then relativity, all of that is already done. So I just have to take proper quantum basically. So that's good. That way we have some time in which we can complete good details.
Yes,
Chalo.
sir. Maybe हमने किया था.
That's right. Anyway, so please give me POQM, people. Okay. So how does it work with physical quantities in classical mechanics in general, people? Like if you want to find out, there's a comment here. So we have read a whole semester but not understood, but now only 15 lectures, everything is clear. Array. Best compliment. Thank you. So I told you since beginning since classical that it's easy. Just believe and go with the flow. Attend the lectures. You will understand everything. So happy to know. And still, the more happiness is still remaining. Okay. This was only the teaser you can say. The good movies. Because obviously, proper quantum we are just starting now. So yes, we're going to have more fun now. Okay. So people in quantum mechanics, in classical, or basically anywhere in physics, forget classical, anywhere in physics, whatever we want to study, how do we start a process of studying it? First, we define a physical quantity. The first step is defining a physical quantity. Suppose if you want to study position or momentum or energy, you define it. Okay. The second step is we find the value of it at t equals to 0, initial value. Like you have to give a reference, just like you have 1 meter, 1 second, etc. You need some reference. Okay. So what we do is we find the value of that physical quantity, of p physical quantity here at t equals to 0. So that's our initial value. Okay. Third, and then what we want to do is how that physical quantity varies with time. We want to study the dynamics of it. How that physical quantity, pq, physical quantity varies with time. So this is the general process. This is the general process of studying anything in physics. Define initial condition and then dynamics, variation of it. So for quantum mechanics also, we are going to learn it the same way. So far we have understood. We have defined the psi. In the whole previous chapter, we have just defined the psi. And now we want to understand how do we find its initial value in different cases and then how it varies with time. In this chapter, we are going to learn the second and third thing. Definition of psi is very well understood so far. Okay, all the properties also around it is also understood. Okay, so let's start with the postulates. This chapter is all about defining the initial conditions and then proceeding ahead with the variation of it with time. Next.
Something. So that year-wise development of quantum mechanics, that the first time on beginning classes, that is after one scientist and that's one scientist, is possible. If it possible, please do it, sir. Please correct the.
So you're telling me that if at all, if I can give you those things in written, like how orderly things are.
Yes, sir,
mostly we have taken everything your wise, but still I could give you everything in pen down notation. Okay. For your curiosity. Sure, absolutely, I will do that. No problem. Okay. So where was I? Postulates, people. So let's start with the first postulate. Please give me state of a system. State of a system. Okay, so we already know state of a system is represented by a ket vector. State of a system is given by wave function psi 1, psi 2, psi 3, and they represent by ket vector. Represented by ket vector. You also call it state vector because it represents state, and hence you call it state vector. Okay, so something like this, psi of x, absolutely. Okay, and it must exist in Hilbert space. That also we know. It must exist in Hilbert space. Hilbert space we already know it is nothing but a linear vector space. Along with that, what do you say? Hilbert space. Along with that, scalar product. The scalar product must be defined. Okay, good. Next, in this also we are just continuing the state of the system. The wave function that we have must be well behaved. Now, people, you may have, I think, learned this statement in BS. It's a very popular statement, but the significance of this is too massive. By the way, again, this is a good MSQ where they can ask which are the properties of a well-behaved wave function. It becomes a good theoretical idea question people. Anyway, so what is a well-behaved wave function? First of all, it must be single value. Tell me.
So hard it more times, but don't understand what is will be.
We will understand it. It must be single value first of all. So like if you are defining psi 1 itself should have one value. Okay, psi 2 itself should have one value. It should be single value. You're not defining wave function for degeneration. Like a wave function cannot be expressed in multiple ways. That's what we are saying. It must be single value. So that's fine. Second, okay, which is it must be finite. It must be finite. Now listen, you have come across this, but the use of this is, when you learn those potentials, you have learned step potential, barrier potential, all those different potential equations. This is where this statement comes into picture. You don't realize this. For example, I'm sure you must have come across an equation, where you write a size a raised to x and then maybe b raised to minus x, and they tell you that a0 or b0. Why? It is related to the statement. People understand. When you say it must be finite, so suppose if you have a function, I'm just giving you an example right away, where a is e raised to x. Okay. Suppose you have a function, but they have also mentioned that x can take any value. If x can take any value along x-axis throughout, there is no boundary. It's not a bounded, it's not a 1D box where x is finite from 0 to x. It's just a wave function along x-axis. Like transmission is happening. You have learned those things where incident rays are there and then there is transmitted rays, let's say in region 2. But then it can go until infinity. There is no boundary given to x basically. If there is no boundary given to x, it means what will happen people if x tends to infinity? What will happen to psi?
0.
No,
It's undefined.
It becomes infinity. It becomes infinity. This is not defined. Psi becomes infinity. It becomes infinite. But what did we just say? It must be finite. It means can this exist? It cannot exist. It means the constant value must be 0. The constant value must be 0 so that this term is eradicated then and there. The value of a must be 0 people. So I think in those problems of step potential, you also have another equation. Suppose b raised to minus x. This is not becoming 0 by the way. Now this is not becoming infinite. Because if suppose you are going in the forward direction from x equals to 0 to x equals to infinity, substitute any of them now. There is no problem here. This is still finite for both the values. What is e raised to 0?
1.
1. And what is e raised to minus infinity?
That is
0.
0. So that's fine.
0.
0 is finite people. 0 is finite. 0 is not infinite. 0 is finite. So this will exist, but this cannot exist because this becomes 0. So you can write that this second value that you have, b e raised to minus x. This is b e raised to minus infinity, which is b upon e raised to infinity, which is b upon infinity. Anything upon infinity is 0. 0 is a finite value. It means at x tends to infinity, wave function is becoming 0. That is fine. That is fine if wave function becomes 0. It's not infinite at least. Okay. It means a will be 0, but this will exist. People. This can exist. This can exist. It is allowed to exist. It means your answer when they ask you to relate this and they tell you answer should be only this. Only if you have learned BSc Schrodinger, you understand that where this is used. But don't worry, we are going to use this when the time comes when we learn step potential. I'm just giving you hands up already, so that later when we learn step potential, you understand that it comes from the definition of the well-behaved wave function. Understood, people?
So the function must be that type of, that is if you put the value, anything value of x in case of x, it has to exist.
Anything else, you have to give limits. So like if it's transmission, then it's 0 to infinity. If it's reflection, then it's 0 to minus infinity. That is, and reflection, then it's 0 to minus infinity. So depending upon what kind of things are happening. See, if it's 0 to minus infinity, then what will happen? Tell me, who will become 0 and who will not? 0 to minus infinity. If it's reflection,
b 0 हो जाएगा.
In that case, this will be 0, no? Because if x is minus infinity, then this becomes infinity. That is b must be 0. Understood? In reflection, please. Clear?
Also there is no transmission. इसे लिखा था. अभी पता चला.
So yes, and hence they used to say that if at all, like if that's the condition, so obviously reflection is happening, so transmission cannot happen. Absolutely. Good.
Yes, sir. अभी तक तो क्वेश्चन ही सॉल्व किए थे.
Chalo, understanding it better. Proceeding ahead, people. Next, property number C. I hope your operators tell me now. Okay? Right now, A cannot exist. Infinite, it means the first cannot exist. A must be 0. This is the condition. Must be. This cannot exist. Okay? And you can write down the range is given to you, by the way. They have to give you the range. So, like this is transmission, then 0 to infinity, like that. So, range is given to you. So, you check the boundaries. You check what happens at 0, what happens at infinity. And if the wave function is becoming infinite, that is not possible. It must always be finite. So, if wave function becomes infinite, that particular coefficient you have to eradicate then and there. Clear? Shall we proceed?
What is the significance, physical significance of infinity of wave function? Because you can't find the particle.
No. It's not probability. It's wave function which is becoming infinite. So, amplitude of the wave function would be infinite that way because wave function is a sine of something. Amplitude would be infinite. Intensity is infinite. So, a lot of things can go wrong now. So, okay, proceeding ahead. Next. That will be like catastrophe, UV catastrophe, infinite intensity or whatever. Anyway, third property of a well-behaved wave function. Again, you have learned this, I'm sure, that the wave function and its partial derivatives must be continuous. Wave function and its partial derivatives must be continuous. Again, this statement is going to go a long way later, people, when we learn whatever the step potentials and everything. What is the meaning of this? Again, like I said, you will have boundaries. No? Like you will have, let's say, a boundary here. This is the incident region and reflected region. Incident, reflected, both can happen here, correct? And this is the transmission region, people. So you have region 1 and you have region 2. This is region 2 and this is region 1. Okay. So when you say wave function and its partial derivatives must be continuous, even at the boundaries. Even at the boundaries. Now this can help you to solve the question, people, solve the constants. See, what we usually do, we have a Schrodinger equation. What do you do with the Schrodinger equation? It's a differential equation, dou square upon dou x square. So you solve the differential equation, you'll get a solution. So what you will get psi is, let's say, C1 sin omega t plus C2 sin omega t, something like that. But then you have constants C1 and C2 now. How do you find those constants? You need boundary conditions, correct, to find the constants. I repeat, Schrodinger equation is a differential equation because what Schrodinger equation has dou square upon dou x square. So it's a differential equation of second order. Next, you solve that equation. You will end up getting a solution. Psi is something. Let's say a e raised to kx plus b raised to minus kx, or a sin omega t plus b cos omega t, whatever. You will get a solution. But then the value of a and b are constants. You want to find them. How do we find them? Using the boundary conditions. How exactly? Sir, but there are two constants. We require two equations. Exactly. Now, wave function and its partial derivatives must be continuous. It means at the boundary, people, at this boundary, let's say this is x equals to a. Suppose the boundary is x equals to a or x equals to 0. I'm writing a equal to b. People, the value of the wave function in the first region at x equals to a, you have to equate that value of the wave function in the second region at x equals to a. This will give you one equation. Derivative of the wave function in the first region at x equals to a, you have to equate this with derivative of the wave function in the second region at x equals to a. Continuous means what? Equal, no? Continuous means what, people? That at this point, whatever value this had, same was this had. That is the meaning of continuity at the boundary. Both of them are sharing the same value. It's not discontinuous, people. So the
Slope
value
equal.
here should be here, the value here should be equal to the value on the right side. This way you can get two equations and you can find the constants C1, C2 or AB. Make a note, please. Okay. Understood? Well behaved. Nice. Okay, people.
So discontinuity means what we are reading mathematics, the function to be continuous, that time, no?
I think, for example, you have a wave function, it's going or whatever. Continuous basically means what? Like if you say at this point things are continuous, okay. So values on the left and values on the right should match with each other. Like in mathematics also you have done, for example, if you have a straight line equation, it suppose it cuts a parabola or hyperbola, whatever. So at this point they are continuous here. So it goes like this and it goes like this. So both the values, the equation of this curve should match the equation at this point. For example, I can create an example right now. For suppose I've got y equals to x square and y equals to x. They are continuous at 1, what do you think? This is y equals to x,
Yes, sir.
and this is y equals to x square. So they're continuous at 1, 1. Something like that. Just telling. Okay. Or suppose you have 1 upon x square, whatever. So even if you like this, y equals to x square, don't you think this is 1 upon x square? And they will be continuous where? They must be continuous at 1, 1. No? This is y equals to x square cover up. This is y equals to 1 upon x square cover up. Continuous means at boundary, they both will share equal value. But in what is in this world, in our well-behaved world, even the derivatives are also equal. In the well-behaved world, I don't know how things will pan out here. Don't relate this with quantum. In quantum, if you say well-behaved wave function, so it means even derivatives are also equal. I did not say that these are well-behaved or not. This is just to understand the meaning of continuity. Clear, people? So we can stop here. It was just a small introduction. We'll continue with postulates of quantum mechanics in the next class. Hang on, don't leave yet. So today is 30th December. Tomorrow is 31st December. We are not taking the class. Day after tomorrow is 1st January. We are not taking the class. From 2nd January we have a class. 2 days I'm not here. But in order to compensate, tomorrow is Friday, Friday one have a holiday. Saturday evening I'm taking an off 1st January, but I will compensate that class. So Sunday morning you have a class at 6. So Sunday we have the lectures morning and not evening. So that will compensate our hours. A very happy new year in advance. And
Same to you, sir.
next year is going to be significantly massive in your life. I understand that. But even otherwise, people, even otherwise, I hope and wish that everything better happens with you all. But even otherwise, if everything best happens, I'm with you. If it doesn't happen, I'm still with you. Post our we will be in touch also. I wanted to do one thing. I wanted to make my New Year very special. So, like you already have an email address, you already have this. So I just need you to send your testimony on this, like whatever you have done so far, how you have felt about it. So whatever you write, I just want to keep it as a testimony of the records of the students whom I have taught personally. Later, actually, Iranka will also ask you to give your testimony, but that will be related to the Iranka in general, right? So this I just want to keep it for myself. So don't tell me about how it is going overall. Just tell me how the lectures are going and everything. Please leave your testimony here, if possible, by today or tomorrow, so that I can feel good before I start with them. Okay. Thank you so
Okay,
much.
sir. Thank you, sir.
Thank you.
Thank you, sir.
Happy New Year, sir.
Thank you, sir. Happy
Thank
New
you,
Year.
sir.
No problem.
Happy New Year, sir. Thank you,
So
sir.
how you celebrate?
Happy New Year, sir.
Tell in brief.
Well, I'm on a date tomorrow. Okay. With not, I don't have a girlfriend, but I have a crush with whom I'm going to go out. But it's only until it's a dinner date. After that, I'm going to meet my best friends, like 2 besties, whom I'm with since my school. So at 12 a.m. usually on a New Year, I'm usually close to years. So yes, that's it. Being frank with you all, as frank as possible.
Yes, sir. I am surprising. What are you saying? How much time? I am getting surprising.
I'm completely fine. Okay. Shut up.
Okay, thank you. Thank you.
No
A lot of
problem.
Thank you, sir.
time.
Yes, sir. Thank you, sir.
No problem.
Thank you, sir.
No problem. Shall I line the session, people? Okay.